Okay, so welcome back, and for this, okay, I follow my director on the back. Okay, so it's really my pleasure to introduce the second and last speaker of today, that is Professor Rodolphe Sepulchre, who's originally from Brussels, so it's nice to introduce him in the Brussels Institute for Advanced Studies. So Rodolphe is one of the most well-known control guys in our community. He was for a long time a professor in Liège, then he moved to Cambridge, and now he's in between Cambridge and KU11. Am I also saying all right? He won several international prizes. He has been editor-in-chief of some of the most important journals of our sector. And I think he's the only person that I know who got a 2 ERC advanced grant. So it's something that I think it's really worth to mention. So I'm very happy that you could join us today and to interact also with our fellows and with our junior fellows and our participants. And it's really my pleasure to leave you the stage.
Thank you very much. Thank you for attending this second seminar in the day. It's indeed my first visit to the Brussels Institute for Advanced Studies, and a particular pleasure for people being born in Brussels to speak in this institute. I think that the program that you are running is very thought-provoking and very important, that to alert the control community that the real problem of the time is indeed to address sustainability. The question that I wanted to address in this talk is mentioned in the abstract, is to what extent can we regulate without calibrating, which I think of somewhat of a synonym of another question, which is how do animals regulate? And the reason is that we have a lot of evidence that the animal world is extremely variable. Not two animals are equal, and if you zoom down to the neural circuits, you see huge variability from circuit to circuit, from neuron to neuron, it's everywhere. And yet animals regulate quite precisely, in fact, much more precisely than most machines do in a lot of tasks. And so it is a bit of a mystery from a control viewpoint to think how this is possible. And if you know anything about regulation, you might have heard of the internal model principle, which is a fundamental principle of regulation theory. And it always struck me that the internal model principle had so much influence in control theory and also in neuroscience. It's really one of the concepts and principles that is shared between those two disciplines. And yet, if you look today at any publication, either in neuroscience or in control theory, talking about the internal model principles, looks like they're talking about completely different things. So you cannot avoid a feeling that the two disciplines have sort of diverged from each other in what they do out of this fundamental principle. So it's also sort of because I've been working with neuroscientists for more than 10 years now, can we perhaps revisit the internal model principle in a way that is more aligned between neuroscience and control theory, and what is that we can gain from looking at how what the internal model principle means in neuroscience if we want to design machines that regulate in a better way. And I would like to think that all these questions are very neuromorphic. Now, I don't know who in this audience has heard the word neuromorphic before. Can you raise your hand? Or is it the first time that you... Yeah, so that's what I expected discussing with during the lunch. And so I decided to include a few slides about neuromorphic. And I'd like to spend the first 10 minutes of my seminar talking about what neuromorphic means. And not with the intention of making my seminar longer, but I will cut the more technical part that I had included in my seminar. So neuromorphic because I think that we are facing today in engineering, information technology in particular, what I think of the AI gap, which is this big divide that we have created between physics and algorithmics. And that the left column is everything that goes back to the 19th century, and the right column is everything that started after 1950, after the invention of the computer. And for instance, you see regulation on the left, that's a word in my title, and you see automation on the right. So from a control perspective, we have created a big divide between regulation and automation. Nowadays, they have different conferences, it's different courses, and I'm always struck how much I'm teaching basic control courses, so I'm talking about regulation, and how much it is confusing for students to, but why do we talk about regulation, not about automation? And clearly, if you think about any animal task, don't ask me to tell you what is regulation and what is automation. Every animal task is a mix of regulation and automation. We have created this strong divide between the continuous, what obeys the physical laws on the left, and the algorithmic, what obeys discrete automata on the right. Now, there is a reason for that, is that we were not entirely satisfied in the physical world doing regulation, because regulation is not reliable. And fundamentally, digital computation was invented to make computation reliable, so that when you compute twice, you get twice the same answer, which never happens with analog computation. So you can think that discrete computation and the whole field of algorithmic was meant to make control more reliable, to make information engineering more reliable. Okay? And so asking whether we can make regulation reliable is a little bit asking whether we can get the best of the two worlds. Because nowadays it looks like if you work on the left-hand side, yes, you inherit of the adaptation and regulation properties of the continuous, but you lack the reliability of the discrete. And if you work on the right, it's the opposite. You are working with reliable machines, but they are not very adaptive. Okay? And so, to me, this is what I think of the AI gap. That the more we use digital technology, the more we live with machines and in a society that is reliable, but not adaptive. And we suffer all from that. Okay, so that is sort of the bigger picture. Now, where neuromorphic comes into the picture, when neuromorphics is really one of the efforts to reconcile those two worlds. And you might have heard of the event camera. If you haven't heard of the event camera, I would encourage you to read an article maybe in The Economist also about this new device that I think is revolutionary and that was first commercialized just a few years ago in 2015. And an event camera works as follows. So you have a pixel, an array of pixels like in a conventional digital camera, but every pixel has an analog detector that detects a change of the intensity of light at the pixel level. And when this change exceeds a certain threshold, it sends an event, it spikes. And so the output of that camera is not a stream of images, each image being composed of a stream of pixels, but instead it is a cloud of blinking dots. Okay? And those dots only inform you about what is changing in what you look at. And yeah, the idea is that this camera is sort of being both analog and reliable. And what does make that combination is the fact that event-based or spiking information has this mixed nature. That if you look at the trace of a spike, whether you measure the voltage of a neuron or whether you look at the events of a camera, you have an analog signal, so it's a physical signal, and from time to time this signal spikes. But you can count the spikes. So somehow, fundamentally, there is something discrete in this analog model of computation. Right? And so that is why event-based information, event-based technology is trying to mix the best of the two worlds, the best of the analog world and the best of the digital world. Now, I said I'm going to say a few more words about neuromorphic before I dig into the details of the talk, but it's a model of physical computation. And physical computation, I will come back to that, but again, it's the idea of using physics to do computation. But you could say it's analog computation, but it's special type of analog computation where you try to retain the reliability of the discrete. Because I think if you don't do that, then you are really going back to the 19th century. Okay, so we should acknowledge the success of digital technology, but we should try to how physics can sort of overcome the limitations of digital technology. And anything that uses this neuromorphic idea is event-based, is bio-inspired, is made of events. And the thing is that we don't really have a theory to design machines that work with events because we have created such a strong divide between analog technology on the one hand and digital technology on the other hand. It's not even clear when we model machines with events whether we should adopt a discrete model or whether we should adopt a continuous model. So that's sort of the idea of spiking intelligence. Computing with spikes, with events, as opposed to computing with zeros and ones. Okay? Now, this event camera that is recently made a cover of Nature, has an article in The Economist 2 years ago. This is a slide that I copied from Davide Scamuraza, who is using this camera to do drone competitions. And he shows the evolution of the event-based camera in computer vision conferences. And also, you see that in the very recent years, all the big players of artificial vision have bought companies the early companies that built those event cameras. So there is really something happening here. It's not the only example of a spiking technology. You might have heard also of spiking neural networks that are very much in the news at the moment. Intel has commercialized this new chip that supposedly computes with spikes as opposed to computes with bits. So, is it the next big thing in AI? So you see that this idea of computing with events is also penetrating now machine learning and artificial intelligence. But where does it come from? So it was all conceived by Carver Mead in the late 80s. And Carver Mead was a professor in Caltech and had spent the first half of his career in CMOS technology. So he was really at the forefront of the development of digital technology and making the chips ever smaller and ever faster. And I think he was one of the first to sort of foresee that this scaling up of digital computation would not go forever. He formulated Moore's law. But he formulated Moore's law exactly to make people aware that at some point Moore's law would saturate. And we are exactly living in that time. Okay? And so certainly we see that I had one more slide, but it's fine. Was showing the limitations of digital, but essentially Carver Mead's vision was that, okay, if we compare the chips and we compute any form of animal intelligence, there is something wrong in how we do digital intelligence because animal intelligence is so more efficient, and in particular energy efficient. And nowadays, okay, if you have listened to the news in the very last days, you hear how much we are begging for more energy to let the progress of artificial intelligence continue. But, I mean, to me, we have reached a very strong limitation. So we are not going to make any further progress because nothing can grow exponentially for very long. Okay? And we have reached a point where we cannot grow with the digital model anymore. Okay? Because we are not going to build nuclear fusion facilities to provide the energy for the data storage center. So we need an alternative. And I find this quite remarkable that the name physical computation was coined as the title of a new course that was created in 1982 in Caltech. 1982 is 15 years after the invention of the computer. It's even before the first personal computer, which I think appeared in 83. And already those physicists were, creating a course trying to think, okay, how can physics address the limitation of digital computation? And there were three of them: John Hopfield, Richard Feynman, and Carver Mead. And 1 year later, the course split it into three, and Carver Mead became the father of what we call nowadays neuromorphic engineering. Richard Feynman became the father of what we call quantum computing. And John Hopfield, I think, became the father of what we call nowadays neural networks and Ising machines that you might have heard. And I think it's quite striking that those three models of computation are more or less the only three alternatives today on the table to address the limitation of digital technology and the energy crisis of digital technology. So I'm not going to talk about the links between the three. I think there are very strong links between the three, but I want to put neuromorphic computing as part of this effort, which is the difference perhaps is that quantum computing is very much physics-inspired, quantum physics-inspired, but of course neuromorphic computing is very much biology-inspired. Okay? And starting from the observation that animals only compute with spikes. I think that this is very closely connected to the topic of the theme of your year. This is the editorial that I published just 1 month ago about efficient control. And I'm listing a number of questions there at the beginning of that article that all were inspired by working on event-based control. And I also want to acknowledge that Carl Åström is the father of event-based control. He wrote the very first paper on event-based control in 1991, together with Carver Mead. That paper has 35 citations today. Okay. But that paper was visionary. So how many pulses do you need to control a DC motor? That's the question that is addressed in Carl Åström's paper. How much interaction with a chaotic system do you need to stabilize a system? This is a very old idea that comes from physics. How much energy do you need to control chaos? There were lots of papers published in the 80s about that question. How many bars do you need on each encoder before you can synchronize two motors? So, of course, if you think of an encoder, we think of an encoder as measuring a continuous angle. It doesn't. We just use the mean field of this encoder. But encoder is a pulse, is an event-based sensor that tells us, when the angle has changed by more than a fraction. Okay. How much energy is required to balance a pendulum? Again, very few papers have addressed that question, and we just published a paper that is neuromorphic control of a pendulum, trying to address this question from this event-based perspective. What I'm trying to advocate in this article is that the concept of minimum energy control is a very old concept that goes back to the optimal control. But somehow, what you learn in optimal control is that when you do LQR, you can tune a parameter that either penalize the control energy or penalize the output energy. If you don't penalize the control energy at all, you end up with cheap control, or you end up with high gain feedback, which is very intuitive. And if you put all the penalty on the control energy, you end up with what we call minimum energy control. And the point that I'm making in this article is that I would say if you go today to a control conference, 99.9% are on the side of cheap control, high gain feedback, very highly performant control, not paying attention to the power of the controller. There is very, very little work on minimum energy control. So maybe it is a time now to, pay more attention to energy efficient control. And often, in my experience, energy efficient control is less intuitive than high gain control. Because, of course, high gain is brute force. And we know that brute force, it's not also very satisfying aesthetically to control a system with brute force. You like to interact with the system as little as you need for the system to do what you want the system to do. Okay, that's really in the spirit of, and that's why this event-based idea takes, again, most of the energy efficiency, not so much in how you implement the control, but how rare you make the interaction between the control and the system. And of course, the less you interact with the system, the more energy efficient you are, in a sense. That's sort of intuitive. Okay, that was a long detour, but perhaps to connect to the theme of your year. And now I'd like to come back to, one of these neuromorphic questions, which is regulation versus calibration. And perhaps you will see that even that question is also related to energy efficiency. Now, I'd like to start from an experiment that I have not invented, that was invented by Eve Marder, who is an experimental neuroscientist. And she did that experiment first in the early 90s. And she took a circuit made of two neurons that you have on the left. And those two neurons inhibit each other. So it's sort of a motif that is very well known in neuroscience. It's the fundamental motif of oscillation. So this is how you build an harmonic oscillator, if you wish, if your material is not a physical material, but a biological material. Has been studied for more than a century. And you see that each neuron can burst. Burst is several spikes and then a period of silence. And when one neuron bursts, it inhibits the other neuron. And so when the burst stops, the other neuron is released from this hyperpolarization, and it rebounds, it bursts, and then you have a sort of ping-pong rhythm. So it's a very robust manner to build an oscillator. And this oscillator is quite robust to parameter variations in the components of the oscillator. It is the basis of all the rhythm that can be generated autonomously in the body. Okay? So this circuit has been studied to death. We have very good models for this circuit. We know about everything of the ion channels that participate in these basic bursting phenomena. And here is the experiment, that you cut the link between the two neurons and you replace one of the two neurons by a computer. And so you can measure the voltage of the neuron and you can inject a current. Okay? And now you ask a question, and I like to think of this as an imitation game. I could say that I have understood this very basic circuit the day where if you look at the behavior of the neuron, you cannot tell whether it is connected to another neuron or whether it is connected to a computer. And we are far from that. So, you read in the media that the imitation game is long won by the machine, that now that we have ChatGPT. Maybe. What I want to point out is as soon as physical interaction is involved, we are nowhere in the imitation game. Okay? And so to me, again, this is another expression of this AI gap, is that when you want your artificial intelligence to interact with a physical machine, we are not very far. And I guess if there are robotics experts in the audience, you will ask, grasping task, any interaction, we have not made much progress since the 80s. Okay? So this is a very, very basic question. And I'd like to start from this question to think of this question as a regulation problem. And I would like to argue that if you use regulation theory as we have developed it in control to solve this problem, you face a problem that it's not about the model that you need. So somehow it's sort of evident, right, that you want the computer to mimic the effect, the behavior of the neuron. So you need to have a good model of the neuron. That's not the problem. We have that model. The problem is the variability of that model. The fact that that model changes from one neuron to another neuron, and that's what you think of the parameters of that model, those parameters keep changing. Even in a single neuron, they keep changing. So if the solution of the problem is to make your computer to match the model of the physical neuron, you face the problem of calibration, because what should you calibrate? You cannot say that the real neuron has a true set of parameters. So you need to match these parameters that continuously change. And you cannot calibrate it somehow. And any calibration solution will fail in the experiment. Currently, we are redoing one version of this experiment where we take the two neuron circuits and we change the temperature. And so these circuits are very sensitive to temperature. So they start, but yet there are lots of regulatory mechanisms in the neuron that stabilize the behavior of the circuit even if the temperature changes. And if you try to reproduce that with the computer replacing a neuron, we are still very bad at doing it. So that's showing a very simple example where when parameters change, it's very difficult to keep track of those changes if you rely on a calibration solution. And the fact that neuromorphic has not made much progress since the 30 years the idea has been put forward is there. So if you read papers about neuromorphic engineering, people try to reproduce circuits in silico. So this is an example, which is a variant of my imitation game, where instead of connecting the computer to one neuron, I'm trying to mimic the behavior of these two neuron system in silico. I'm trying to reproduce that on a chip. And this is an example where, a paper where people have done that. And also there, if you look at the solution, it's a calibration solution. So you fine-tune the parameters until you match the desired behavior. That's a calibration solution. And the problem is that whenever you apply this on an analog circuit, you do the same set of parameters in the next circuit, it doesn't work. There is too much variability. You are hit by the inherent variability of the continuous world, of the analog world. So is regulation possible without calibration? Is a bit, can I make analog computation reliable? It's a bit of the same question. Okay. And my experience is that it's hard, both if you work with biological neurons and if you work in silico. Okay. And the answer that I want to propose to overcome this problem is very simple, is to say we need to move away from regulating trajectories. All regulation theory that exists today is about regulating trajectories. So trajectories, for instance, in the case of my example, would be the voltage trace of this neuron. So it's had a few spikes, then a silence, then another few spikes. If you try to track that trajectories, you need calibration. In fact, I can prove that you need calibration. And you cannot calibrate. So my naive proposal is to say, don't try to match the trajectories. Only try to match the events. And the events here are quite clear. It's on, off, on, off. That is what you want to match. But you want to match that precisely. So you want your circuit to be on for the same duration as the burst and your circuit to be off for the same duration. Okay? So event regulation doesn't mean rough regulation. It means precise regulation, but not of the entire trajectory. Precise regulation of waypoints. And now if you start thinking about any animal task, that is how it is solved. An animal never regulates a trajectory. An animal regulates waypoints. So if I reach something, if I grab something, it's an event. And close to the event, there is a lot of precision. But between the events, I never do twice the same motion to reach an object. But I reach it very precisely. And so if we want to be sort of neuro-inspired, the solution to the difficulty of calibrating that is suggested by nature is don't try to regulate the trajectory, only try to regulate events. But then regulate the events precisely. Yeah? And so I want to share with you, it's a very simple idea, but it's an idea that somehow is different from the regulation theory, because regulation theory is always about regulating trajectories. You do a path planning for a robot, and you path the trajectory of the robot. You don't path waypoints. So I want to share with you, I will not go very deep in the technical details, because I won't have time for it, but I'd like to give you a few hints of what I've learned from neural circuits that I think could be imported in control theory to implement that principle even in artificial machines. So what I will do is that I will very briefly summarize what is meant by the internal model principle, in case you have not heard of it. And then I will go very quickly on the second part, which is how we apply this theory to the toy example that I have. So how can you think of this imitation game as a regulation problem? But the take-home message there is that if you use the models that exist for those neurons, it's not a hard regulation problem. You can solve it with the existing theory. But you can solve it in theory. That is assuming that you can calibrate. Okay? So if you accept to calibrate, the solution is easy. If you don't accept to calibrate, there is no theory. That's my message. And then I want to explain to you two insights from neurophysiology that I think could be incorporated in the existing theory of regulation to fix it, to make it possible to regulate without calibration. And hopefully this can be applied to any regulation problem. So this is the initial paper that started the theory of regulation, 1976. We are celebrating the 50th years of this article, and there will be a special issue in the magazine about it. And it's essentially formulating a very simple regulation problem. You try to design a controller to track a reference signal and to reject some disturbances from the environment. And the point is that the reference signals and the disturbance are generated by the environment. So they are modeled by this exosystem in regulation theory. And so you try to design the controller so that you can regulate the behavior of your system to this environment, either to reject a signal from the environment or to track a signal from the environment. So, and what you read in the introduction of this paper is that you can solve this problem in two steps. On the one hand, you need to make sure that the feedback system is stable. And when you close the loop, well, you have to pay attention to stability. But once you have proven stability, then you can look at the steady state behavior to what the signals will converge asymptotically. And there you face a second problem, is that you must make sure that in steady state, when there is no regulation error, your system is able to generate exactly the right behavior. So now, what is the main result of this paper? It's the internal model principle. And what does it say? A regulator synthesis is structurally stable. So you see that the regulation only makes sense if you assume that there is uncertainty. If there is no uncertainty, it is an inverse problem, and there are lots of disciplines that solve inverse problems. What makes it a control problem, a feedback control problem, is that if there is uncertainty in the plant and in the controller, only a feedback solution can solve the regulation problem. So you assume uncertainty, both in the plant and in the controller. And structural stability is a way of formalizing this robustness to the uncertainty of the plant and the controller. So what this says is that you can be robust to the uncertainty of the plant only if your controller uses feedback, and if in the feedback loop you can generate internally those signals that you want to reject from the environment or that you want to track from the environment. So this internal model principle is the idea that you need to be able to generate internally in your brain those signals that you want to track or reject in the environment. And that is a necessary condition. You see, there is a only if in the statement. And it is the necessity of the internal model principle that makes it quite interesting. Regardless of the solution that you choose, you cannot avoid doing that. So let me illustrate that on a classroom example. You have just a first order derivative. So y dot equals u. Derivative of velocity is force. And you want to reject a disturbance, an additive disturbance d. So what should be your control, your feedback control? Well, maybe you can try minus ky to stabilize. You want to achieve y equals 0. And then you want to compensate for the disturbance by minus d hat, right? Well, in steady state, so your closed loop system is stable, right? And in steady state, when y equals 0, well, y equals 0 only if d equals d hat. You see that you must be able to generate d hat. That's what your controller is going to generate. But your d hat, you are going to solve the regulation problem only if d hat equal to d. D is given by the environment. Now, how do we solve that? Well, we make some assumptions about the signal d, about the exosystem. And typically we say, if the derivative of d is 0, I have a constant signal. And how do I reject a constant signal? I need an integrator in my control. That's integral control. So integral control is the simplest example of an internal model. You assume that the signal that you want to reject is generated by constant signals. You put an integrator in the controller, and that gives you the way to generate any constant signal. Right? And so integral control says you cannot reject constant disturbances unless you have an integrator in the controller. That's what we teach when we teach regulation theory. Okay? That's perhaps the only thing that students remember from their control class because it's so important. Now, it might happen that your disturbance is, so a typical case is the disturbance is an harmonic signal, not a constant signal. So now you can use the same principle. You generate your disturbance with a second order differential equation, and somehow you need a copy of that equation in your controller. Well, here you already have a parameter that omega naught is the frequency of this disturbance. You must know it exactly. Okay? And then if you look at the way people have generalized regulation theory, well, you could say that my disturbance is produced by a dynamical system, x dot equals f of x. And now I'm very general. And what the internal model says is that your controller needs to have an exact copy of that system. How is that possible? That's the calibration solution. Because the current answer that you hear in conferences, put a big, deep neural net and trail the network, and it's going to work. That's a calibration solution. So because learning means that you are going to match the d hat to d. Okay? And that doesn't work in practice in any system where d itself is changing and constantly varying. So the internal model principle says that there is no regulation without calibration. You cannot regulate unless you have an exact model of what you want to regulate. And this principle not just holds for the regulation problem, it holds for any control problem you hear about if you attend a control conference. Synchronization, coordination, observer design, name it. They all rely on the same implicit assumption that you must be able to calibrate. Okay. Let's now apply this to my imitation game and see that the solution of the imitation game is very simple from a textbook. And I'm going to skip the details here, but you are going to trust me that, okay, my exosystem is now this behavior that I want to reproduce. So it's the biological interaction between those two neurons. My plant is one neuron. Okay, that's the system that I'm trying to control. And my controller is the computer program that imitates the other neuron. And the feedback loop is my electrode that measures the voltage and injects currents. Yes, it's a very physical scenario of. And the steady state property is that I want to design the controller such that this feedback loop reproduces the exosystem. Okay? And the feedback regulation is that I should design the controller such that somehow it can synchronize exactly with the exosystem. Now you can sort of imagine a cartoon solution, which is that this inhibitory-inhibitory interaction in neuroscience is described by, so a circle denotes a neuron, and an arrow with a dot denotes inhibition. So you see that the motif is two neurons interconnect with mutual inhibition. That's my biological oscillator. I'm reproducing this by connecting the plant, which is one neuron, to a controller, which is a model of my neuron. And I'm replicating the interaction between the two, the feedback loop, also as mutual inhibition. And then I'm adding this arrow with a little arrow there, and that means excitation. And that means that I need to somehow to see my reference signals so that it can entrain the synchronization of the controller and the. So from a sort of a cartoon perspective, it's very clear that if your plant controller interaction mimics the reference generator and has a little bit of excitation in between, those systems will synchronize. And the part that I'm going to skip is that if you convert this motif into the mathematical equation that we like in control theory, it still works exactly the same. That is, all the assumptions that you need to make the solution of the regulation problem easy, they are always satisfied with those models. Relative degree 1, minimum phase. If you know about regulation theory, you will recognize sort of the properties that makes regulation easy. And then what you can show is that in this example, neuronal regulation, you solve this imitation game if and only if the plant plus controller is an exact copy of well, I'm sort of, it's a bit tautological, this statement. Huh? But what is, I think, the important part is that regulation theory tells you that you have no choice of copying exactly a replica of the neuron that you want to imitate. And it's a necessary condition of the theory. So if you believe in regulation theory, there is no escape. Okay? And so then the question is, but how do animals do? Because animals cannot regulate. If you go and measure the parameters of a neuron, of any two neurons, you see completely different parameters. So what's the trick? What I want to say is that the trick is that they don't regulate the trajectories. But they still regulate enough of the trajectories to match the event very precisely. How do they do that? Okay. That's what I want to share with you that I've learned from neuroscience. Okay, I haven't talked about adaptation. Of course, I'm not saying that there should not be adaptation. Neurons do adapt all the time. So there is internal adaptation. And adaptation is part of regulation theory. Adaptive regulation is somehow very natural. And so the synonym of adaptive regulation in neuroscience is neuromodulation. And neuromodulation is extremely important. In fact, it is the whole career of Yves Marder to understand neuromodulation in neural circuits. And there is a beautiful parallel between what we call adaptive regulation and what is called neuromodulation in neuroscience. But that doesn't solve the problem. So you can, again, neurons happen to be the easiest system to regulate adaptively. They have all the nice properties that we need to regulate the system adaptively. And so when you study this learning problem of how you can adapt a model to match a neuron, you realize that, all the literature that you read in learning, in adaptive control, is about making the learning rule more and more sophisticated to learn more and more difficult systems. But none of this is necessary in nature, because somehow nature has selected motifs that make the learning very easy. So my message is that it's not the learning that is difficult, is what you learn. Is that there is no concept of calibration in nature. Okay? And I think that this is a big bottleneck of control, but also of machine learning today, this idea that you can learn a true set of parameters. Well, perhaps it works in the virtual world, but in the physical world, most examples don't have that concept of true parameter set. Okay. So, what time should I finish?
We don't have, you can go on.
No. When did I start? A quarter to 2?
Self-regulate.
Okay, so let me come to the most important part of the talk, I think, which is what I've learned from neuroscience to solve this problem. Okay, 2 lessons from neurophysiology. So just recapitulating. On the left, we have the classical block diagram of regulation theory. On the right, we have a sort of the textbook's solution that is suggested if you want to solve the imitation game of matching a biological oscillator. And so it looks very close to each other, but there is a difference. And so the first difference that I want to highlight here, which is I think the most important, is that what we call the exosystem, so the exosystem is the model that generates the signals in the environment. In regulation theory, they are of one type, and in neuroscience, they are of another type, and they are very different. So, and I want first, before I explain that technically, I want to show you an experiment that I find the most striking experiment that I've learned, that I've been exposed to in neuroscience. It's nothing novel, This experiment was first done in the 70s, and then it was repeated in 1995. So you take a neuron, and you do electrophysiology, so you inject a current in the neuron, and the neuron is excitable. So if you inject a current, the neuron starts spiking. And that's what you see on the left, that there is a step change of the injected current, and that you see that the neuron starts spiking. And you record that spiking for a certain time, and then you stop the experiments, and then you redo the experiment. And so you do the same experiments 15 times with the same neuron in the same laboratory conditions. And you superimpose all the traces. And what you see is that the first 2 traces are more or less aligned, but very quickly, they are all over the places. So the phase of this oscillator, if you wish, is not reliable at all. The same neuron, same experimental condition, you do it 5 minutes later, you get a different phase. That's the inherent variability of the analog world. And if you record the spiking time, on the second plot, you see that the first spiking times is a line, but very rapidly it's all over the places. So that has motivated neuroscientists to say that spike timings is irrelevant. The brain cannot use that information because it's so unreliable. There cannot be information there. It's a debate that has been going on in neuroscience for 50 years. Now what you see on the right is a slight modification of the same experiment. Instead of injecting a constant current, you inject a jerky current. But you repeat 15 times exactly the same input. So it's a frozen noise input experiment, as they say. And now the spikes are perfectly aligned over the 15 trials. What is the magic here? This is very defeating. And this has led to all sorts of speculations that noise is fundamental to reliability of information and that it's an emerging property and whatnot. I'm going to say that there is a very fundamental but very basic distinction between those two experiments. Think that my exosystem is modeled by a differential equation. And that what I see on the left is a limit cycle oscillation of this differential equation. Well, a limit cycle oscillation of an autonomous system, it's an analog system, it's a physical system, it cannot be reliable. And the phase variable of a limit cycle is never stable, by definition. So you never have, if you know about Lyapunov exponents, so you have strong stability of the limit cycle, but on the limit cycle, you have, by the time invariance of the solution, any shifted solution is also a solution, and there is no stability that forces one solution versus the other. So somehow this drift, this phase drift, is inherently a property of noisy differential equation. So there is nothing surprising on what you see on the left. It's the unreliability of analog computation. What is the trick on the right? The trick on the right is that this input, what you see is no longer a limit cycle. What you see is a sequence of events. And each event is generated by the input signals crossing the threshold. So you have an excitable system, and each spike is the excitability of the system that manifests itself. On the left, you only have one event, a long event. And you have the response to that event. On the right, you have a sequence of events. And now, an excitable system that you hit with a little kick, that is very stable as an object. So if you do it twice with slightly different conditions, you get twice the same explosion. So if you wonder, so this is the experiment that was done 20 years earlier. It's even more striking how reliable are the spikes. Those are recordings. Huh? This is us redoing that experiment in silico with neuromorphic circuits and making exactly the same observation. So the unreliability that we have in biology, it's also in any analog circuits design. And so this is the cartoon that sort of explains the difference. If you know about phase portrait, you have an equilibrium that is the dot that is stable and has a small basin of attraction. If you are pushed outside of the basin of attraction, you have a large excursion before you come back. That's the phenomenon of excitability. So you see that the way you generate events in an excitable system is you give a little kick to the system so that you get out of the basin of attraction and whoops, you have these big swings before coming back. That behavior is a stable behavior that is very contractive, very stable, very robust. And what you have on the right is the same system, but when you change the applied current, and now you have a limit cycle oscillation. This limit cycle oscillation has lost the excitability property. And you have no stability in the phase. But the point that I want to make is that in regulation theory that has existed for 50 years, all the exosystems are generated as closed dynamical systems. So the only non-trivial trajectory that a closed dynamical system can generate is a limit cycle. So by definition, the exosystems that we use in regulation theory are unreliable. And what we see in biology is that the way it is fixed is that you generate the same limit cycle, the same rhythm, not with a limit cycle, but with a repetition of little kicks of an excitable system. So if you only look at the oscillation, you don't see the difference. But in one case, it's very reliable. In the other case, it has no reliability. So excitable event generators are contractive. Limit cycle generators are non-contractive. And that's a general statement. And so immediately you see the striking difference that as a default assumption of regulation theory, the exosystem is generated by an autonomous differential equation, therefore non-contractive. Whenever you apply this theory in neuroscience, the model that you try to imitate is an excitable system, so it has this contraction property. So why not taking inspiration and modifying our generator of system to generate excitable trajectories as opposed to. The second lesson that I've learned from neurophysiology is as simple, as defeating, but perhaps slightly better known, is the fact that the coupling or the feedback, the regulation that in control law is using the error regulation as a feedback. So that's called diffusive coupling. It's never that type of coupling that you see in biology. In biology, you have synaptic coupling. And synaptic coupling it's a different type of coupling. I'm not going to enter into the details, but the result is that when you couple two oscillators with synaptic coupling, miraculously, the events synchronize, not the trajectories. And why is that? Well, because synaptic coupling is such that away from the events, there is no coupling. So it is a sort of a coupling that is only active during the events, and during the events, it's very strong. But it's very strong for a very tiny amount of time. And if you compare in a model of two heterogeneous neurons, the effect of synaptic coupling, you get event synchrony, and then you do instead diffusive coupling, as we do in control theory, because you try to synchronize the trajectories, you completely squash the two oscillators, because you force them to have a sort of the same mean field. And that's something you never see in nature. Okay? So you see synchronizing the trajectories as opposed to synchronizing the events. Somehow, when you combine excitable generators and synaptic coupling, which is the only way neural circuits work, you solve a very long-standing problem of regulation theory, that how do you synchronize the events without calibrating? Okay, I think I will finish here. I will sort of wrap up with, first of all, the idea that, so what is, I would call this neuromorphic regulation. So it's a regulation revisited after looking at those neural circuit experiments. The first thing is stop regulating trajectories. Instead, regulate events. Events are waypoints on the trajectory. So when you formulate the problem, define the waypoints that matter and regulate those waypoints. Don't regulate the trajectories. The second point is that your exosystem that generates the tracking signals should be excitable models as opposed to oscillator models. And the third point is that the feedback regulation should not be diffusive, it should be synaptic. And if you do that, the rest is most classical. So you use all the theory of regulation can be leveraged. We don't need to invent a new theory. And that's what is quite remarkable about this neuromorphic system, that sort of sit at the intersection of the two worlds. Why are they physical? Because they are modeled as by differential equation of chemical reactions, mechanical. So they obey the classical physical law. They are modeled by differential equation. So therefore, they fit the theory of regulation. But they are very special type of physical models. They are very special in the sense that the only thing that they can do is to generate events. And that makes them very special. That makes them possible. That makes it possible to model them as discrete systems, as automata. So these neuromorphic systems have the unique property that we can always regard them as automata or regard them as physical systems. And I think that's the reason why we so easily get to the best of the two worlds. Now, you could say, but is this just of relevance for neuroscience? This is just explaining the scientific questions how animals regulate. I think it's very relevant for engineering science. And so this is why we wrote this paper about revisiting one of the most classical regulation problems, which is regulation of a pendulum, and showing how the idea of controlling the pendulum exactly as children control a swing. You don't control continuously the trajectory, you just kick the swing from time to time. Okay? That's exactly what you can implement with this regulation architecture. And I'm not going to spend any time on this, but the only point that I want to make is that the internal model that I'm using in this controller is not an internal model of the pendulum. It is the same clock that I've been discussing in my seminar. So it's a biological clock. And the only role of that biological clock is to predict the sequence of events that I need to swing my, to push my swing at the right amplitude and frequency. So it's not an internal model of the trajectory, it's an internal model of the events. And for that reason, I get a lot of flexibility. I don't need to be even close to the dynamics of my pendulum. I only need to replicate the same sequence of events. So I think this is how animals regulate. And I'd like to finish this talk by quoting the original formulation of the internal model principle that is attributed to Kenneth Craig. And Kenneth Craig formulated that in 1943 in a book that is called The Nature of Explanation. And this is what he says. Only an internal model of reality, this working model in our minds, enables us to predict events which have not yet occurred in the physical world, a process which saves time, expenses, and even life. In other words, the nervous system is viewed as a calculating machine capable of modeling of parallel external events, and this process of paralleling is the basic feature of thought of an explanation. And it had never occurred to me until recently that Kenneth Craig doesn't talk about trajectories. He only talks about events. Thank you.
Thank you, Rodolphe, for this very inspiring talk. I imagine there will be a few questions from the audience.
Thank you very much. This was very inspiring. As Emanuele asked for crazy ideas, I have a couple of comments that might also be stupid, but
please.
Please bear with me. The first one is that I think with this perspective, you provide a sound theoretical background for morphological computing in robots, because it's common to have actuators made of materials, and we usually say, well, we save computation because there are some aspects that you cannot control. But it is just a fuzzy motivation, and I think in this perspective, now there is a strong theoretical background for justifying and motivating morphological computing. And the second is maybe an hazardous analogy, but the need for an internal model that capture the essential elements of what is going outside seems to be one of the main principles of the free energy principle. Do you see any connection between this work and that?
Two questions to the point. Very nice. Thank you for those questions. Well, the first question, indeed, when I think about robotics, I, of course, think about soft robotics. And the fact that the fundamental bottleneck of soft robotics is that we create robots soft so that they are more adaptive, so that they can be regulated. But then we need to control them, and we cannot control them reliably. So I think that the bottleneck of soft robotics is exactly the same issue, that we cannot regulate reliably. And I keep hearing soft robotics is saying, but we don't want control in soft robots. We make them so physically intelligent that they don't need control. And I very much share that perspective, except that they still need control. Because animals regulate precisely only because they can, if you look at an octopus, the motion of it is completely physics. But at the time where it grasps something, it's very precise. And that is an event. So there is a lot of control, but control is at the time of the event. And so if you think about rehabilitation robotics, it has been a sort of a fundamental paradox for the last 40 years, the same thing. You don't want the machine to force, you want the machine to be compliant, so you want very low impedance control. This is at the expense of accuracy. Because the moment you want accuracy, you stiffen the control, you stiffen the impedance, you make high impedance, and you lose the softness, you lose the compliance. How does event regulation solve that? By controlling sparsely in time, so minimal interaction, but when it interacts, it's very strong. So it's high impedance, it's high gain control, just as a result of the excitable nature of the controller, but it's so restricted in time that on average it's a very low impedance control. So I think indeed this is a perspective to solve the bottleneck of soft robotics, I think. Now your second question is that indeed I think that there is a complete alignment between the theory of Friston, of the free energy principle, and the internal model principle. I think that Friston's theory is how machine learning has reformulated regulation theory in the model language of Bayesian modeling. So it's sort of a statistical perspective that, I respect because it's expressing a principle in a different language. What I'm trying to do here is to demystify this theory. That I think that animals regulate in a very, very basic way. So you can call this inference, you can call this active inference, you can call this regulation, choose your language, but at the end of the day, the learning part is almost trivial because the architecture is so constrained that the only motion that is possible are these events, and the only interaction that is possible is this excitable interaction. And that part, I don't see it in the theory of Friston. So you can make a very general theory of regulation, but it doesn't it doesn't answer the question, how do animals regulate? So I think that it's very consistent with the theory, but that there also you need to address how do you regulate without calibrating. Yeah.
Are there other questions?
Just a curiosity. Your presentation was very nice, very inspiring, but also a bit provocative. So accept a provocative question from my side. So I was wondering if I really like the idea of controlling only when it is needed, so on an event based with the high energy and very limited in time. I was wondering if from a control energy perspective, so assuming that the energy that you use to control a system is one of the elements to keep in mind. I was wondering if at the end it's not the same, the energy expenditure, let's say, controlling in a sparse way, very energetically, or control it, let's say, in a software way, let's say, continuously in time?
Very nice question too, thank you. In fact, I'm thinking of this question, and I think that the only proof is a proof of concept on this pendulum. So now we are building a pendulum, and we want to compare different control laws and sort of prove or disprove that this event-based control strategy is way more energy efficient. And so I cannot present the result, but just to say that this is, I find a very interesting question. I think it's a question that needs to be answered empirically. And if we can make a point on a model that is as simple as the pendulum, there is a big hope that this will scale up. I'm not pleased at all, maybe I should cut the microphone here, by the current development of spiking neural networks, where the perspective goes in completely the opposite direction, where you spike like crazy and you use the mean firing rate as the information. So I don't see any sparsity there, and I don't expect any significant gain of energy efficiency there. I'm convinced that the reason why animals are so efficient in computing is because they minimize computation. The vision is so selective that the one bit of information that you transmit is only the one bit that you need to actuate the machine. Okay? And so it is in the selection of the information that reduces the computation. Which is completely at the other end of the spectrum of what we currently do, where we absorb billions of information, we know most of it is totally useless, and then we spend another billion of computation to identify the information that we need in this big nest. So this is what is very wrong, I think, in the current direction of AI. See, always more is better. We have reached the limit of what we can do with more.
That's a very good point. Thank you for your answer.
So, thank you. Is some other question? Frank, then closing.
The nice thing about BrIAS is that you can ask naive or even stupid questions, right? So I'll try. When you were giving your talk, I immediately thought about those flocks of birds or fish swimming in a perfectly synchronous way.
Yep.
Does this mean that they don't check trajectories, but only changes in directories?
Absolutely. Well, thank you very much for this question. You know, I started this very long journey in 2002, spending a year of sabbatical in Princeton and working with Naomi Leonhardt, trying to understand exactly that. So we were looking at coordinated motion of animals, which is fascinating, right? We have not reached a fraction of what animals reach in terms of synchrony. And so I've become obsessed by this question of synchrony from that time. And I start developing, as others, a theory of synchronizing, coordinating motions in robots, as it's still a very popular topic. And it's all about synchronization and coordination of trajectories. And then increasingly, I was puzzled that, you never escape the model that if you want a better synchrony, you cannot have too much heterogeneity, and the more heterogeneity you have, the more you have to compensate for the heterogeneity by strengthening the coupling. And you end up with this mean field that is incredibly constrained. And there is nothing more at the opposite of what you see when you look at any recordings, when you look at these fish swarms and so on. It's not a mean field. If you look at the individual trajectories, they're very, very different, but the level of synchrony in the events is spectacular. And that is what is creating the aesthetical emotion, is that there is no synchrony, there is no homogeneity, but there is synchrony. And what is synchrony without homogeneity is an open question, if you look at from a mathematical or control perspective. But I think what fascinates physicists and biologists in synchrony is the fact that synchrony occurs in heterogeneous population. And then you have the possibility of having ensemble phenomena that are not just the reproduction of the single agent phenomenon. The moment you assume all the agents are the same, the only thing that the mean field can do is a scale version of what the agent is doing. That's not what we like in democracy, right? So I think it's a very compelling question of how do you achieve synchrony? What does it mean to achieve synchrony in a population of heterogeneous agents? And that is what's so fascinating about this fish and animal coordination. Yeah. But I think they synchronize events. Yeah.
Okay, so I don't know if there are other curiosities. If not, I think we can close here for today, at least the online part, because then I think many of us will stay here to discuss, chat, having a second coffee, and trying to spend time doing something productive. So thank you all for being here. Thank you again, Rodolphe, for coming and joining us for today. So we can make a second round of applause.
Thank you. Thank you.
And so I give you the appointment to next week, again on Thursday, again at the same hour, and have a good rest of the afternoon.